So let's start. So I only have the daily concept check, just one question for you. What does the second derivative tell us about the function? What does the second derivative say about the function? Anyone, please?
Point of inflection.
Yes, yes, concavity and points of inflection. We're going to go back to the graph because we haven't graphed it yet, but I just wanted to show one thing. If I know that the function is concave downward, this is the function, this is f of x, then the slope of the tangent line, which is the first derivative, the slope here, 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 here, and here. What happens? It's big, smaller, 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 0, negative, negative, bigger negative, bigger negative, bigger negative. So if the function opens downward, the first derivative, its rate of change decreases from big slope to smaller slope to smaller slope to 0 slope, negative slope, bigger negative, bigger negative, bigger negative. Now, if the function opens upward, here is the first derivative. Big negative, smaller negative, smaller negative, 0, positive, bigger positive, bigger positive, bigger positive. So this is f of x. And what I graphed here are values for f prime, from big negative to big positive. So if the function opens upward, we know that the rate of change of this function is increasing on this interval where the function is opening up. Okay, so back to the graph, to the table. So I don't know anything about this function, and I don't care to know anything about this function except this table. Nothing matters anymore. I did all my work. I put everything in here. That's all I need. Okay, so we plugged in 0 and we got 1. Let me just copy the function because I want us to find the x-intercepts. That was the only thing. So where is my function? What was it? Okay, so it's x cubed minus 6x squared, x cubed minus 6x squared plus, I think, plus 9x and plus 1, and is g of x. Okay. I don't need the rest. It will be recycled. Okay. So in order to find the x-intercepts so we can put them in the table, we will have to solve the equation g of x equals 0, as we know. Okay. So we go to the graphing calculator. Allow me to share my screen and share. Here it is. Here it is. Okay, in y equals, we already have x cubed minus 6x squared plus 9x plus 1 because last time we used it to find those y values for different x values that we determined. But now what I really want, actually, so the coefficients are 1, negative 6, 9, and 1. I want to go to apps and number 9 and polynomial root finder. Yes, degree 3, correct. First coefficient 1, second coefficient negative 6, third one positive 9, and the last one 1. Now the calculator should give us how many solutions? Anyone? Mandatory? We don't care, real, imaginary. How many will it give us?
3?
Yes, because the degree is 3. Excellent. So here they are. Negative 0.1. Now this one, the way it looks, it's not a real number. You don't see the end. So let's take a look at it. See, it ends with an I. So it's a real part minus a real number times I. So this will not be, we will not be able to graph this. This is imaginary. And of course the conjugate of this, because the coefficients of the polynomial are real. So if we get x plus I, 1 plus I, we have to get 1 minus I. So that's why these two will be disconsidered. They exist in the sense that the equation has 3 solutions, but only one of them is important to us, negative 0.1. So in the table, I will put negative 0.1, very difficult to plot, but we'll find a way. And I will have to, under negative 0.1, I have to write 0. Of course, it makes no sense. It makes no sense. I have to put it in the correct place. I was going to say, how is that possible? Well, I put in the wrong spot. It has to be to the left of 0, negative 0.1. Good. So now we have everything. We are ready to graph. So first, I will graph the coordinate system. And then I will plot the points. Okay. First point, so I'm just going to use different colors just to make sure that you see the steps. Negative 0.1, 0. 0, 1. 1, 5. 2, 3. 2, 3. 3, 1. Okay, ready. Slowly but surely from left to right. Function comes from negative infinity when x goes to negative infinity. Okay. Somewhere here. Negative infinity, negative infinity. It goes up, increasing to the x-intercept, opening down. Again, when x approaches negative infinity, y approaches negative infinity. So then, somewhere here, increasing, opening down till the x-intercept. Continue to increase to the y-intercept, still opening down. So I realized that this is a better shape in order to reach those 2 points. Good. These are polynomial functions. If I have to twist my wrist to graph them, something is wrong. I can't do this and this. No, it has to be smooth, continuous function. Okay, then it decreases to 1, 5. Okay, so it's increasing to 1, 5. It has to be smooth, no problem. Where it has a relative max. So this is the relative max, 1, 5. So all the way, it was opening down, increasing every step of the way till the relative max, which is here, this point. Then it starts decreasing, and it gets to a point of inflection, which is 2, 3. Decreasing, decreasing to the point of inflection, 2, 3. At this point, it opens up. Continue to decrease to 3, 1, that is a relative minimum. So up to the maximum, down to the inflection point, changes concavity, now opening up all the way, 3, 1, that's the point of relative minimum, increasing all the way, increasing, opening up to infinity. This is the graph of f of x, x to the third minus 6x squared plus 9x plus 1. It's all based on what we learned from the first derivative, what we learned from the second derivative, limits at infinities, negative infinity, infinity, x and y intercepts. That's it. If you want to check with the graphing calculator, that is absolutely fine. I'm going to share my screen, and let's do that. So second and quit, get out of there several times. I know now what I want to see. This is our function, but I'm not going to click on graph. No, I'm going to adjust the viewing window because I know exactly what I'm looking for. I'm not looking for negative 10 to 10, negative 10 to 10. There is no need. The left-hand side of the y-axis, negative 2 is good enough. The right-hand side, 8 is good enough. Scale of 1 is okay. Y minimum, negative 2 is good enough. Y maximum, I know it goes to the maximum of 5, and then beyond that, okay, let's say 8. So I made my adjustments based on the graph that I already have, because I know exactly where the action is. That's where the action is. Let's click on graph now. Here it is. So very difficult to see that negative 0.1, very difficult. Then it crosses at 0, 1 as we expected. It goes up to 5, 1, 5, right here. It comes down and no one can identify this. We can, because we did the work. Right here at 2, 3, there is an inflection point. Opening downward, and from here on, opening upward. It comes down to a relative minimum of 3, 1, 3, 1, and then it goes on forever to infinity. Again, how did we discover all this? From critical numbers, from studying the sign of the first derivative, from inflection points, when the second derivative is 0 or undefined, from studying the sign of the second derivative that tells us opening downward, opening upward. Positive, negative, positive says the function must increase, the function must decrease, the function must increase. Now there is one called second derivative test that I would like to talk about. You can use it or you don't have to. It's up to you. So let's suppose I don't study the sign of the first derivative, which I think it's silly. But let's say we don't study the sign of the first derivative. We don't know when the first derivative is positive or negative. But I know that the function opens downward, and there is an inflection, and there is a critical number at 1. So the function opens downward, and there is a critical number at 1. What can this point be? 1, 5. So the function opens downward. I did not study the sign of the derivative. I know the function opens downward, and I know that there is a critical number at 1. What can 1, 5 be? What can it be? The function opens downward, and somewhere here, between negative infinity and 2, there is a critical number. What can it be?
The maximum.
That's it, a relative maximum. Let's look at the other side. I did not study the sign of the first derivative, assuming I was in a hurry to get the second derivative, and I did not study the sign of the first derivative. But I know that the function opens upward, and I know that there is a critical number at 3. What can 3, 1 be if the function opens upward and there is a critical number there somewhere? What can 3, 1 be?
A relative minimum.
Absolutely, because the function opens upward. But I think it's silly not to study the sign of the first derivative and just go directly to the second derivative, because if you make a mistake on the first derivative, then you carry on the mistake to the second derivative. So when I finish with the first derivative, when I study the sign, I always check to see whether these two rows work well together. If they don't work well together, then I have an error, and when I get to the second derivative, I will carry that error into the second derivative. But that is called the second derivative test. So if there is a critical number in an interval and the second derivative is negative, then this critical number turns into a maximum, relative max. If the second derivative is positive and there is a critical number in that interval, then that critical number turns into, or that ordered pair is a relative minimum. And that is something called the second derivative test. We're going to write it down. Any questions about this? We're going to graph out the functions, of course. Any questions about this? Sorry, I meant to finish this last time, so you have the whole explanation and graph together with everything, but I talked too much. So sorry about that. Okay, any questions for me? Anything that you would like to continue with? If not, I will choose. Okay, I want to go back to the book. And I would like us to choose a gibberish one. So let's look at any gibberish. Again, why am I doing this? Who cares about this? Once we understand the table, or we practice with a gibberish, then the table becomes even clearer. That's why I would like to choose one. So from 35 to 38, you choose, or I will.